This is all the information we actually have on these guys. These are all of our dang it. These are all of our subjects. Okay, these are age at death. Some of them are pretty old, 90, 93, 95. Male or female, race, one, they're all one, so I'm assuming all Caucasian. Whether they spoke Spanish, 2 probably means no. Education level, highest level of education. And then we have all these cognitive scores, which are specific. So we have the MMSE, which is that basic test that Donald Trump did amazing on. That's like, where are you right now? This is still used a lot, but it's not really telling. And these, you can tell that these are all pre-AD because the scores are high. So the highest score is 30. And we only have 1 or 2, sort this, 30, 29, 28, 27. We have a few, 25, 26. Some of these, like, maybe the person didn't know what day of the week it is. And honestly, if you're retired, that's kind of normal. These are more specific cognitive scores, and I don't know what these numbers mean because I'm not a cognitive tester, so it's something I would have to look up. So it has global cognitive, last valid. So last valid just means the last appointment. The genotype, this is specifically ApoE epsilon allele. So you may have heard of ApoE. This is pretty important in Alzheimer's. 4 is really bad, 2 is really good, 3 is like the standard of what most people have. I have actual percentage numbers on that if you were interested in that. But these guys have like 1 bad allele, 1 normal allele, and then these guys at the bottom have 1 good allele, 1 bad allele. Missing data just means we didn't have the data for that. Okay, these are more cognitive scores. And then we have more stuff. PMI is postmortem interval. That's how long the brain how long after the person died before the brain was taken or sectioned or preserved. So something like that. Postmortem interval. So from death to when the brain was taken out. And you just kind of would check to see that these aren't long. If you had one subject that was like constantly off and he had a PMI of 33, then maybe you would throw that out in the results. You don't have to worry about that stuff, but that's why we have it. The brain weight, so you know how much the brain weighed, which is not necessarily what was in the person. It may or may not have been, but I mean, this is also dependent on like height and weight, just the size of the person in general. So we don't really worry too much about that. But it's the same thing if you had one person that was constantly, like, just their numbers were way off. They were throwing off the group average. And you came back and you looked and you saw that the brain weight was different. Maybe there was something going on there, like the way the brain was preserved, you know, it was more dehydrated, or I don't know. Because we're looking at RNA, maybe some degradation occurred during processing, and that's why we got weird results, or a lot of the sequencing maybe was from PCR amplification because there was degradation, so it would skew the results. Again, you don't have to worry about that, but we just kind of look for outliers, and I just color code everything or use these bars that tell me everything so I can know quickly. So like if I sorted this, the way the bars go down. Anyways, SARAD, BRAC, NIA, Reagan score, we have other stuff, stroke, ALS, and a bunch of other stuff. So if they had, generally the groups that Elliot gets are not comorbidities. So generally you won't have like Parkinson's and AD, stroke and AD. I don't know what specifically this means for stroke, so I'm guessing this was documented in their medical records as the person having a major stroke. The truth is, as you age, you have a lot of strokes. It just kind of happens. Sometimes anyone looking at your brain, sometimes They won't know that until after you die. It might be obvious that there was a stroke. Usually it's not something you check for unless you're being used in an AD study. But if there were a lot of like mini strokes or several episodes of stroke, it would probably be classified as vascular dementia or AD/vascular dementia, and it would not be used in this study. So that's just something to know, that these data sets are usually cleaned for comorbidities. So the Brack score, which is what we're dealing with, and then SARAD. You mentioned Thal. Is Thal SARAD? Do we have Thal? Like I said, we usually work with Brock. We'll have to look up, see. I can't remember off the top of my head. So we have a lot of information for these guys, which is nice. You don't know any of this until the end. I guess at the step where you're doing differential expression analysis, you would start to know this because you would have to divide the groups. You could do ApoE differences. You could run differential expression analysis on those. Another thing you can do is, after you get the counts, you want to normalize them in some way. So remember how I said we don't know if this person has 4,985 because they had a lot of reads sequenced, or if this is just how many copies of the transcript for A2M they had. So we want to normalize it in some way. A common way to do that is to just divide this by total number of reads. Sometimes you'll take into account the transcript length, because there's some ideas that longer transcripts are more likely to end up in the final results, are more likely to be sequenced. Sometimes that's truer for some data sets than others. Don't worry about these ideas unless, I don't know. I don't know what kind of questions you're gonna get. Just know that we have to have some way to normalize them. I'll tell you the best way, and you'll work with it. But once you normalize these numbers, you can actually work with these numbers. So these are the raw read numbers. So instead of running differential expression analysis for all of the different groups, you can actually go in and compare across groups. So you would get like a mean average or a median average and run statistics, especially if you're interested in a certain gene. So like I said, A2M is actually a relevant gene for Alzheimer's disease. Here it is here. So I would have, how many people do we have? 26? Yeah. 24? We're at 26. So I would have 26 different numbers for A2M. Here I only have one because I'm still compiling, putting everything in the spreadsheet. But I can actually go through and normalize this A2M number and compare it across subjects or across groups. And sometimes this guy has 10,000. Wait, what is? Yeah, 10,000. So that 5,000 may not have been high. Normalize these copies and then do the comparisons with these read numbers, meaning you don't have to do differential expression analysis for everything. I will tell you exactly what to do. Yeah, that's more information than you need, I think.